Hello everyone, my name is Adam Eubanks, and today I'm going to be talking about an empirical neural network transport model fit to a large DIII-D database. Alright, so for the outline of this presentation, first we're going to look at the importance of modeling turbulence. We're going to look at the TGLF model, also the DIII-D transport database, and how we compare that with TGLF. And then after that, I'm going to show you how we designed a TGLF saturation rule, captured those experimental fluxes from the data set. We're going to look at the candidate functional forms that we used, and then also how I used neural networks to find an experiment-based saturation rule, and finally the fully analytic form for the saturation rule given to us by symbolic regression. Okay, so first it's important to talk about the importance of modeling turbulence. So put simply, turbulence is the process by which energy, particles, and momentum are going to be transported from the center of the tokamak to the plasma edge. And so in order to model this turbulence, generally gyrokinetic models have been used. However, these models are very, very computationally expensive and therefore not always practical. And so what TGLF does is it's a reduced model that is efficiently predicting this transport by relying on a couple physics assumptions. So let's talk about the TGLF transport model. Basically, it's predicting energy, particle, and momentum fluxes in the tokamak plasma. And the idea behind this, and you can see this is given by the image that we have to the left, is that the transport of a turbulent plasma that has reached saturation is going to be able to be predicted starting from the linear growth rate spectrum of the first few most unstable cases. And so what TGLF is doing is it's linking this linear growth rate spectrum to the transport fluxes using a saturation rule. So that's really the key that we're trying to find here. And so this is much more computationally efficient compared to the full gyrokinetic models by several orders of magnitude. So that's super, super helpful. Now let's talk about the DIII-D database that we used and the TGLF transport fluxes. So we developed a database. Basically it has 2,500 discharges, 9 time slices per shot, and 9 radial locations per time slice, and we filtered that down from 200,000 cases all the way to 100,000, and then we ran TGLF on these cases to validate the TGLF fluxes against the experimental fluxes to see that everything was working properly. And if you want to know more about that, you can see Tom Neiser's talk, and then we extracted the quasilinear weights as well. And so the goal for this is really the question that we're asking is, can we design a TGLF saturation rule that best matches the experimental fluxes observed from DIII-D? And then once we get that saturation rule, what can we learn from it? So in designing this saturation rule, we looked at some functional forms. So first we know that from gyrokinetic simulations, that the energy spectrum of turbulence, it should have a peak at low k, and you can sort of see looking at the graph to the right of you. And we chose a simple functional form for the saturation rule that is satisfying this observation, and that's given by ISAT is equal to A over ky to the c times 1 over e to the b times c over ky. And so in this equation, the a, b, and c coefficients are free parameters, with A representing the amplitude, B representing the position of the peak, and C representing the speed of the decay. Alright, so from there what we did is basically I built a neural network that is finding the A, B, and C coefficients as functions of the various plasma parameters that we have from our database. So right here what you see is we have a huge correlational matrix where basically I plotted the correlation between every single plasma parameter and itself, and these black bars represent the A, B, and C coefficients. And in order to reduce the number of parameters, basically I removed the parameters that are either very highly correlated or very negatively correlated, just to give symbolic regression less work to do and make sure that we were displaying things properly in the way that we are training our model. So going on to the TensorFlow graph, basically what we're doing is we're starting from random A, B, and C coefficients, then we're computing the TGLF fluxes, and then we're comparing those to the target experimental fluxes, And then we're updating the A, B, and C coefficients, computing the TGLF fluxes, rinse and repeat. And that's given by this chart you see to the right of you. And so then in training that, what we did is first I had to upgrade TensorFlow from 1 to 2, and then I ultimately decided on a dense neural network. Looked at a couple different topologies, and the reason why we chose a dense neural network is because it's faster, simpler, and it's going to be more interpretable because it's simpler, which is going to be better for symbolic regression to take from the weights from the neural network in order to form an actual equation. So the output of this neural network is going to be the A, B, and C coefficients based on the plasma parameters. And the parameters that we decided with are listed right here. Also, at the end of training, we plotted a test flux output to the flux target. So this is on a log plot, and ideally the two would be perfectly correlated with each other right on this line, but you can see they do get pretty close. And as for actually training the neural network, we have our cost function and our epochs, and we plotted the cost over epochs for both the training set and the testing set, and you can see the two are almost identical and converge nicely at the end. Now, how did we apply symbolic regression to this? Well, basically we want a fully analytical saturation rule. So what we did is we took from the neural network coefficients of A, B, and C, we tried to see if we could find some sort of equation that would model those outputted coefficients. So if you see right here, we have our neural network. The outputs of our neural network, those A, B, and C coefficients, go into symbolic regression, which from there would give us a expression for representing the coefficients. So in order to make things easier for symbolic regression, we decided to take the log of both the A and B components, and we kept C the same. So the first thing that we looked at was scikit-learn, and we just did some brute force polynomial regression. After that didn't work out too well, we looked at genetic algorithms. So gp-learn is a Python library that does genetic algorithms, which is really useful for doing symbolic regression and finding equations from data. And then we also looked at Eureka, which no longer exists, but it did help. And finally, we looked at simulated annealing, which is a special technique for optimizing functions. And we used TuringBot, which is a software that does that very well. And from the output of TuringBot, we got the following equations. So you can see A, B, and C are roughly equal to these three equations. And then all we would do is from the database, we would take these equations, plug them in for the A, B, and C coefficients, and then see how well they fared. So some important things to note. We compared the log of the A coefficients from the neural network to the log of the analytical coefficients, and you can see there's a nice correlation there. Now for B, something interesting that we found is that it kept on going to this constant of around 0.02, and we'll have to look more into that moving forward. And for C, as you can see here, there's also a correlation. And it's important to note that these are heat maps. So obviously the lighter, like the yellow, means that there are more cases in that area, and the white and the purple mean that there are less cases in that area. Alright, so now with the regression plot, basically what we did is we plotted the flux output and flux target as seen in an earlier slide where we talked about the training of the neural network, and we plotted the neural network, and then on top of that we plotted the fully analytic model. So as you can see, for the most part, the green and the blue are both pretty close to each other up until the end where they both diverge, and that's something that we're going to need to look into. Also, we might want to look into the theoretical underpinning that is allowing the success of these data-driven equations, see what's going on there. And we're going to need a large nonlinear gyrokinetic database for comparison as well. So some other next steps, we're working on more data filtering to make sure we don't have any outliers or inconsistencies. Also addressing the overprediction of the higher fluxes as shown here. Looking more into the B coefficient, why is it a constant? And looking more into the high flux cases for both the neural network and the fully analytic expression. But yeah, that's pretty much it. So thank you guys for attending my talk.